And I can unmute my mic and then this.
And then I think it should be fine, no?
Yes.
Let's do like this.
Hmm?
Can you?
W-
It sounds loud again.
Does it work?
Yes, but now it's loud, like crazy.
It's loud again? I don't know.
No. Try. No.
Now I hear you guys over Zoom.
Okay. Does it work? Is it too loud?
Not over Zoom. I'm listening over
No,
Zoom.
it's good. Okay, perfect. Then I mute my mic here. Just a second. Where can I mute the mic?
You don't need to mute it.
I don't need to mute it, but
No,
the Zoom mic I don't need to mute.
No, because they want to hear you.
And this doesn't. Okay. Okay, good. Perfect.
Welcome back. So I will be chairing the session this afternoon. By the way, so for the speakers, there is the link of the Wi-Fi. Please use it. And also, you have to log in to the YouTube channel or to the Zoom. So please try it before so that we don't waste any time. So it's my pleasure to introduce André Eckardt. He comes from the Technische Universität Berlin, and he will speak about controlling quantum systems by driving on dissipation.
Yes, thank you very much. Yes, and thanks the organizers for the nice invitation to Konstanz. Today in my presentation, I will consider clouds of quantum matter that are in some structured environment. And this structured environment could be an optical lattice if we talk about ultra-cold atoms, or it could be superconducting circuits if we talk about photons. And these systems shall be driven out of equilibrium by time periodic driving. And additionally, they are coupled to some environment, which could be a thermal environment in one case and an engineered environment in another situation. Let me start with a very general motivation for what I'm going to present. So if you have driven dissipative systems, why would you have a look at them? I mean, if you look at thermal equilibrium, everything is, you have this universal concept, which is statistical mechanics, which can be very helpful to predict observables and compute observables of systems. You have Gibbs states, for instance, and then you can use statistical mechanics. In turn, if you are driving a system out of equilibrium, there is no such universal concept. And you have to solve, for instance, equations of motion to predict what these systems do. And this can be often a challenge, but hopefully, as I will try to convince you, this can also be an opportunity to control states and properties of systems beyond the very strict constraints which actually equilibrium provides. And let me just start with a simple example, which is just a container with liquid, which is heated at the bottom and cooled at the top. So think about just a kettle on the stove. And then if you drive it weakly, you have a small temperature difference, you don't heat it very much, then you have heat transport via conduction, but locally you still have thermal equilibrium. On the other hand, if you start driving stronger, there might be convection going on, and you get a qualitatively new behavior. And similarly, also for quantum systems, if you drive them out of equilibrium in a driven dissipative fashion, you might get interesting novel states that you stabilize by controlling the system in such a way. We are going to consider open Fouquet systems. So these are time periodically driven systems which are coupled to an environment, let's say a thermal environment here. And one can argue that, or if you use standard methods as one Markov theory, there is a variant for Fouquet systems. You can derive a master equation of this form where you have the coherent evolution generated by the Hamiltonian of the system, and you have a dissipator which scales quadratically with the system bath coupling. So this is typical master equation you get, and then you can argue quite generally if you go to the limit of ultra weak system bath coupling, and at the end of the talk I will talk about how to go beyond this limit and consider systems beyond this limit. But let's now stick to this situation where the coupling between system and environment is small compared to the level spacing in the system. And in this case, your steady state will always be diagonal in the Floquet modes of the system, which are sort of the generalized stationary states of your Floquet Hamiltonian. And if you had a non-driven system, this steady state would be diagonal in the eigenstates of the system. And the reason is quite simple, because if you let gamma to 0, the steady state should be a steady state of the coherent evolution. And it is a steady state, and each of these states here in the sum is such a steady state of the coherent evolution. However, the dissipation is not unimportant still. It does two things. On the one hand, it drives the system into this state, because when you start from a pure state, it might not be a statistical mixture like the state which is written down here, and the off-diagonal elements have to decay, and this can be induced by the environment. And at the same time, also this probability distribution, with which probability you find the system in which of the quasi-steady states and the Floquet states, is determined by the dissipation. And in this limit of ultra-weak system-Barth coupling, it is determined by a simple classical master equation, where you have golden rule type rates for a transition from a quantum state M to a quantum state N. And you have, of course, two rates. So the population or the probability for being in state N increases for the rate bringing the system from M to N, and it decreases with a reverse process. If you now have such a driven system, it is a non-equilibrium situation. And this is reflected in the fact that these rates can be written as a sum, and each of the terms in the sum correspond to processes where the Barth energy changes by minus the quasi-energy difference in the system plus an integer multiple of h bar omega. And if we had a non-driven system, this would be the energy difference, and only the mu equals 0 term would matter. However, in the Floquet system, there are photon-assisted processes where the drive provides or absorbs energy quanta of h bar omega. And that means the same transition in the system can be induced by processes where the energy in the Barth increases, or by processes where the energy in the Barth decreases. And in this sense, you can see that Floquet states actually do not have a sharp energy. And you cannot say there is a Floquet state sort of which is energetic. I mean, you can say it's energetically higher or lower, but you can't really order them according to their quasi-energy. And this is reflected in this property. And as a result, you do not have a relation like this, that the rate divided by the backward rate is just given by such a factor depending on the inverse temperature and the quasi-energy difference. If you had a single term in the sum, this would be true, but you have many terms. And if you compare this now to thermal equilibrium, in thermal equilibrium, you exactly have such a relation with respect to the energies in the system. And as a result, you can solve this master equation, the steady state of this master equation down here easily by choosing the Gibbs state, the thermal state. And for this state, each of the terms of this sum vanishes independently. And the terms of this sum actually correspond to the net probability current from state M to state N. So if you have, let's say, you take this picture here, you have your quantum states 1, 2, 3, and you have the probabilities for being in them, then the net probability current or the probability current between two of these states from one to the other, they just cancel each other. And this is what we know as detailed balance. And if you now go to the driven scenario, this is not true anymore because this relation is not fulfilled anymore. And now the probabilities have to be solved by just solving this equation. And each of the terms in generally is non-zero of the sum. And so you have net probability currents in the system and detailed balance is broken. And most importantly, now the state of the system, which is characterized by these probabilities, depends on all the details of the environment. Here up in equilibrium, it's just a function of the inverse temperature of the environment, and here it depends on the details. And that means if you change your environment, the non-equilibrium steady state into which the system will relax will depend on how you engineer your environment, on how you drive your system. So you have a lot of control knobs to engineer this non-equilibrium steady state into which the system runs. And this is a robust way of state engineering. And I will give you now two examples of such state engineering in Floquet systems. And then I will, in the last part, mention how you can treat these systems if you go beyond ultra-weak system bark coupling. Okay, so the first example I'm going to mention is work together with Francesco Pettiziol, who's a postdoc in Berlin with me. And it's about cooling Floquet systems via cavity-based reservoir engineering. And what we have in mind here are systems of photons in superconducting circuits. So these type of superconducting circuits, if you where you have photons that can occupy artificial atoms or transmon qubits, you can describe them using a Hubbard model, a bosonic Hubbard model. Essentially, you have an attractive interaction, and you have hopping between neighboring lattice sites. And now there is a well-known strategy to engineer dissipation by coupling the system, and I will go into details how this works. How to coupling to the system to resonators, which are driven and dissipative. And in this way, you can address transitions in the system and prepare, for instance, the ground state. You can cool the system to the ground state. On the other hand, it is known, and this is something I didn't introduce right now for the sake of time, but I'm pretty sure all of you know about it. If you drive these type of systems, let's say in a high frequency fashion, you might describe them by an effective Hamiltonian, which is, for instance, the time averaged Hamiltonian of your driven system. And so in this way, you can, for these charge neutral photons in the circuits, you might induce a situation where you have, let's say, such a ladder system, and where you have a magnetic flux piercing each of these fluxes. So this type of driving can be used to effectively change the properties of the system. And this is known as Floquet engineering. And now the question is, can you combine both of these techniques with each other? The answer is, it is not as simple that you can sort of first replace the Hamiltonian by the effective Hamiltonian and then apply these schemes. It's a bit more complicated, but you can still do it. And let me explain you very briefly, just in showing you some sketches how this works. So this is the undriven case. So you have your system, you have a lot of different energy levels. It's occupied by photons. And then you couple the system to a cavity mode. And this is sort of well detuned from the system modes. So you have only virtual particle exchange between the states of the system and the cavity mode. So you have a perturbatively small occupation of this mode here, and you have a decay. And now you start pumping this mode with photons, but it's red detuned. So in order to absorb a photon and then let it decay again, the system needs to borrow an energy of delta, which is the detuning from the system. And if you sort of tune this delta, you can lower the energy in the system and prepare, for instance, in this way, the ground state of the system. And now the question is, how does it work for Floquet systems? For Floquet systems, you can essentially, you have a picture like this, because what I said before, when exchanging sort of energy with the environment, the system can sort of borrow and or absorb, or can exchange photons with a drive. So you have various different copies of your system spectrum corresponding to different numbers of energy quanta h bar omega, let's say, absorbed by the drive. And in this way, you have to, in a description in an extended state space where you take into account all these copies, you can again treat similar processes, but you have to make sure that the cavity mode is detuned from all of these different copies, and then you can repeat these arguments, and you can see that it still works. However, this is something which only works if they are energetic or if the width of the spectrum is small compared to h bar omega, so you cannot scale it up to very large systems. But for finite systems, this is something that works. And then you can show that, for instance, if you have such a Floquet-engineered ladder system, here with 8 lattice sites and magnetic flux, that you can, by adding such driven resonators to the system, you can prepare with a high fidelity the ground state of the system. And you can also do it now for 2 particles on 6 sites, which behave like hardcore particles because of the strong interaction, even though it's attractive. And you can also, with rather large fidelity, it's not very high. I mean, it's 80%, depending whether you consider this high or not, but it still works, and you can prepare the ground state. And of course, this is interesting because if you extend this a little bit and you make it 4x4 lattice sites and you put a small number of bosons, you might use these tools to prepare, let's say, a baby fractional quantum Hall state. We cannot simulate this because it's too difficult, but in principle, this should be possible. Okay, let me now come to a second example. While this example was about preparing ground state-like properties in Floquet-engineered systems, this is now about engineering states which have no equilibrium counterpart. And this work is mainly done by Alexander Schnell, also in Berlin, who is a postdoc in Berlin. And we had support from Arthur Videra, who is an experimentalist. I mean, you know him, I'm sure, in Kaiserslautern. And involved was also Lingna Wu, who is now at the University of Hainan. And this is about using Floquet heating, which is actually a detrimental effect, and I will mention what it is, or it's usually a detrimental effect to induce essentially Bose condensation. So what is this going to be? So we consider an optical lattice system. So now we consider we have about 50 sites, and we have 200 particles on this system, and they are non-interacting. So it's a non-interacting system. We have tunneling. The kinetics is given by tunneling between neighboring sites. And we embed this system in a bath given by another atomic species. In this case, we consider potassium atoms immersed in rubidium atoms, and we do microscopic derivations of the equations of motion for these parameters. And this system in which this 1D system here is embedded is a 3D system, so it's much larger than the 1D system. In that sense, it can absorb a lot of energy also from this 1D system before really this environment or the bath is noticeably heating up. And we assume that it has a temperature which is about, which is 2.4 J. So it's on the order of the tunneling matrix element. And that means it's not a very cold temperature. It's an intermediate temperature. Moreover, since this is a 1D system, actually we wouldn't expect this system of blue bosons, of this potassium bosons, to Bose condense. I mean, if it's a finite 1D system, it can Bose condense, or it can have a rather sharp transition to something which is where you have most of the particles in the ground state. But this happens at rather low temperatures, which decrease with the system size. So the temperature below which this happens goes like 1 over system size in these 1D systems. And now, on top of this temperature in which we immerse the system is also rather hot. I mean, it's intermediate. And accordingly, if we just look at this system, we look at the time evolution, we prepare it in an infinite temperature state, and then we look at the occupations of the single particle eigenstates, and there is nothing interesting happening. It slowly thermalizes to a thermal state which has no interesting features. And now we do something else. We start driving the system additionally periodically in time at one lattice site, or locally would be sufficient, but we just choose to drive it on one lattice site. And we drive it with a frequency which is not a high frequency as it is often used in Floquet engineering, but it's a frequency in the middle of the bandwidth. It's 3/8 of the bandwidth. We drive it strongly. The driving strength is equal to J. And we drive it on the 20th of this 50 lattice sites. And then we see the following. So now we plot the occupation numbers of the Floquet states, and we see there is one Floquet state which actually acquires more than half of these 200 particles on average. So by this type of drive, which actually should heat the system because it's resonant, it induces Bose condensation, at least in combination with this environment around the system. And this is at first glance rather counterintuitive, but you can intuitively understand what's going on. Namely, if you look at the eigenmodes of this system, this is like a discrete version of a particle in a box, so it's given by sine waves. Then there are some modes which happen to have a node where you drive. So some modes decouple from the drive, so they are not driven actually. In that sense, they are like pseudo-Floquet states. So this is the overlap of the single particle eigenstates without the drive, or the maximum overlap of each of the single particle non-driven eigenstates with the Floquet modes. And you see there is a sequence of states which sort of remain Floquet states because they're undriven. So in a way, you can say there is many states from all of these. We have many Floquet states, and a few of them essentially correspond to undriven eigenstates. In that sense, they are like pseudo-Floquet states. And you can also look at the energy fluctuations of the Floquet modes, and these modes actually have zero energy fluctuations, while a typical Floquet state, since we drive resonantly, has very large energy fluctuations. And this is something which resembles a scar state, essentially. I mean, we have a single particle problem here, so it's not a many-body problem, but you have like typical states, which are, I mean, they are not thermalized in the ETH sense, since it's a single particle problem, but they have huge fluctuations since they are driven. In this sense, they are sort of generic. And then you have a few states which are really different, and this is just because they decouple from the drive. And now you can have a look or can think about what does it in combination with a bath. So if you look at the driven modes, okay, so now you can divide your system into two parts. You can think about the driven modes on the one hand and the undriven scar-like modes on the other. And these driven modes, they are the majority. They are rather broad in energy, as we see down here. And you can argue that the low energy modes hybridize on average, if they mix with other modes, with modes of higher energy. So the mean energies, which is this dark area here of the Floquet states, is sort of narrower than the energy of the undriven modes, which is symbolized here by this more lighter shade of red. And this is Floquet heating. So low energy modes hybridize predominantly with higher energy modes. And in that sense, the average Floquet energy at the bottom of the spectrum, if you wish, or the bottom of the mean energies sort of is increased in energy. This is Floquet heating. The undriven modes are the minority. They have sharp energies, and the level spacing is rather huge because they are just few, right? It's like a smaller system effectively. And now what does the drive do? The drive, what does the dissipation do? The dissipation distributes particles rather equally between the driven modes because they're all very delocalized in energy. On average, there is a transport from the driven modes to the low energy modes of the undriven ones, since as a result of this Floquet heating, they are higher in energy, so the bath prefers to transport them from the driven modes to the undriven modes. And finally, the large level spacing makes the bath, makes it very efficiently, helps to transport particles to the lowest energy state of these undriven states. And then you expect a Bose condensate under these conditions, you can expect it in the lowest of the undriven modes, and this is exactly what we find. Okay. In the last, I don't know, maybe 2 or 3 minutes, let me just mention, let me skip this here and let me mention, this is about how to do this. Let me just give you, discuss another topic very briefly. This is about methods for open many-body systems beyond this limit of ultra-weak coupling, which I was introducing at the beginning. So the simulations we did for the examples I showed you before were done in this limit of ultra-weak coupling. For the superconducting circuits, this was possible because the level spacing was big because the system was small. In the second example, it was possible because it was only the single particle level spacing that mattered, and this was still relatively small. But eventually, if you are dealing with many-body systems, you have a level splitting, which becomes very tiny. I mean, it's exponentially tiny in the bulk, and at the bottom of the spectrum where you have quasi-particle excitations, the level splitting is also very small. And so you cannot assume this limit. And that means you will not have a situation where your system is described by a Lindblad type master equation. And so it's hard to justify such a treatment in many-body systems. And especially away from equilibrium, you need, but you still need an accurate master equation to describe your dynamics because it depends crucially on the details of the environment and how the system couples to it. So I just want to raise a little bit the awareness for that this is an interesting problem. I will, and if you sort of think about the master equation that describes your system beyond this ultra-weak coupling, it is associated with 2 problems. And one problem is you first of all have to find the dissipator. And if you think about Bort-Markov theory, this dissipator comes out of a perturbation theory where the system is the unperturbed problem. If you have a many-body problem, this is not an easy task. And if you're away from equilibrium, it's not just fine probably to have just a low energy theory, an effective low energy theory of your system, but you might want to have, you really need, if you do this type of Bort-Markov approximation, all the states of the system. So it's difficult. And then you have to solve the problem, which is also a difficulty. And so now both are difficult. And if you just draw a line where you think about increasing coupling strengths between system environment, then you have this ultra-weak coupling limit for essentially 0 plus a little bit. Then you have a Born-Markov regime, and then you have methods which extend this Born-Markov regime. And very often they are associated with artificially increasing the dimension of your state space by using reaction coordinate mapping, hierarchies of equation of motion, and so on. And this is the last slide, so I will not move any further. So it's, and already this Born-Markov limit is hard to derive because, as I said, the unperturbed problem is the full many-body Hamiltonian. It gives rise to a non-local equation of motion because your eigenstates from which you determine this are actually delocalized eigenstates, which makes it very hard to solve also if using, for instance, matrix product states. It's not of Lindblad form, so there's no straightforward way of unraveling this equation in terms of stochastic equations. And also, it is known that this theory is not even thermodynamically consistent with the thermal state of the total system and then tracing of the bath. So there's a lot of problems. And we have been working in the group on these problems. And let me just mention a few works. One sort of approach has recently put forward by Alex Schnell. So I'm not involved in this. It's Alex is also here in the audience. And it's about to find a local approximation to the Redfield equation, which solves both of these problems. So it doesn't need to diagonalize the full Hamiltonian, and you get a local equation of motion. The second example is work that we did together with Tobias Becker, who was a PhD student in the group, now is a postdoc. And it's about how to unravel such non-Lindblad equations in an efficient way by using quantum trajectories. And a last example is a simple way of sort of extending this Born-Markov equation so that it gives rise to canonically consistent master equations. And this is also work by Alex and Toby and also user Thingna. And with this, I think I should close. Let me come to the conclusions. I wanted to say a few words about the quantum trajectories, but I will not do it. Let me just click through this. It's not too much. So this, yeah. I would just want to come to my conclusion slide. And the conclusion slide says, actually combining driving and dissipation is an interesting tool for state preparation. And you need accurate and efficient methods for simulating systems also by beyond system, ultra-weak system bath coupling. And that I think this is an interesting topic. And let me just at the end make a little bit advertisement because Audit asked me for our new DFG research unit, which will start this fall, and where we will apply sort of open, or we will consider ultra-cold atoms as open systems with the purpose of using them as quantum simulators for open systems, and on the other way around to use dissipation in these systems for state preparation. And with this, I would like to thank you.
The 9 slide remaining minutes, we take one. Yes.
I mean, you have to. I mean, breaking detailed balance is easy. You have to, for instance, if you have a thermal environment, you start driving your system in a Floquet fashion and you break detailed balance. So this is easy. Verifying it is not so easy because you really need to have a system where you know your environment very well so that you can compare it to the theory. And this is why I think ultra-cold atoms are so interesting in this respect, to sort of test actually these type of theories. Sorry? I mean, these theories are uncontrolled in a way. I mean, in some sense, they are perturbation theory in the system bath coupling. And let's say if you go beyond this Born-Markov theory is a second order theory, but the state isn't even correct in second order. So in that sense, you can estimate maybe how big the error is that you expect, but it's not only a perturbative approach. You make other approximations. So I think it's essentially an uncontrolled approximation as often. Yes. Yes. I didn't say any, I don't expect any of this, and I didn't think about it. I just call them scar-like. I mean, they are definitely not scars in the sense of many-body scars, because there's also no real generic states in a driven, this was a single particle problem, right? So they are a little bit like scars in the sense that the typical states have large fluctuations in energy, but these are not thermal at all, right? Because we are not in a thermodynamic